3.5. Okay? And for y, we can quickly make it. So y here should be minus 3.5 and 3.5 here. Okay, I leave you for the details how to work out the two numbers, but that should be back in. So here that is 3.5 compressive, and then compressive 3.5 in clockwise direction. So the strain stress on the top should be in this sense, the magnitude 3.5. Okay, we make one more example to have the Mohr circle cover the origin. Okay, we'll look at this example and say, again, how about do the same thing, we rotate by, again, 98 degrees. Okay. And how about we try the other one? Because I run out of space there. We try this one. Here, we rotate in different ways, 49 degrees. So in this way, we have rotating clockwise by 49 degrees, so x will move to x prime, and y will go to xy prime. So the Mohr circle is, we calculate average first. The average is the sigma x plus sigma y. So for this case, is sigma x will be 2, sigma y is compressive, so that is minus 4. So this is minus 1. The radius equal to sigma x minus sigma y squared plus tau xy squared. And this one, again, here you have to apply the sign convention carefully. So x equal to 2 positive, y equal to negative 4, so minus 4. So this, again, I make up this one, r equal to 5, will be easier for our calculations. So for this circle, r equal to 5, and the center at the minus 1. So here should be 4. This is 5. The center is minus 1 here, and the radius equal to 5. Okay. And this is tau. And now right now we label the x. The x point will be 2 and 4. And the 4 is in this sense. So we can label the x. X will be 2 and 4. That should be here. And y equal to minus 4 and 4. And on y plane, the strain stress is 4 in this sense. So y should be here. And that one is 2 and 4. Okay, now we can work on the angles first one more time. So using this triangle, so from here, this is for this triangle here, that one using, this is 4, and then here is 2. 2 plus 1 equal to 3. So therefore, this is again 53 degrees. So from here, we label it. So here is 53 degrees. Okay. So with this one, again, we rotate 49 degrees clockwise. So here we rotate is 98 degrees. So we rotate 98 degrees. So that will go to here. This angle is 98 degrees. And so again, this is rotate clockwise, so we rotate in 98 degrees. So here is our x prime, here is our y prime. So 98 degrees plus 53 degrees equal to, so here again, this is 45 degrees. Okay, so once we have the 45 degrees, my drawing is not so perfect, but here we can utilize this triangle. So for that triangle, this is 45 degrees, and this is 90 degrees for the blue one. So the radius equal to 5, so this side will be 3.5. So therefore, x prime has the coordinate sigma. The first coordinate will be how much? Can you read? This is 1, this is 3.5, so the s coordinate has minus 4.5, right? Again, I'm talking about is the coordinates from here to here. That is 1 plus 3.5, so that's in 4.5. And here is in the negative range, so we put a minus here. And this one is 3.5. And 3.5 is in the quadrant, so we have this one. So we can put this one to here. The first one is 4.5 negative, so compressive. And the strain stress, the value equal to 3.5 is in this sense, in that sense, so the direction should be going there. Okay? And anyone can try. What is this? Probably you can utilize this triangle. And for this triangle, let me draw this one again here. So again, this angle is 45 degrees. So here is 45 degrees. So this is 5, this is 3.5, this is 3.5 here. So again, right now this distance is 3.5. And we're looking for the coordinate from here to here. How much? 2.5. So here, this one is 2.5. And this is 3.5 here. And 3.5, this point is in this quadrant, so it's in this sense. So 2.5 positive, so tensile, and 3.5 here. And that's symmetric to other two planes. So to this one, that should be very straightforward, and to apply the Mohr circles already.
So you can't use the sigma x, sigma y thing, use the sigma y prime. Sigma
Yes,
prime.
the same thing you can do that one. Yeah, either way.
It doesn't add up on that one. 7 and you have 6.
No, here is minus 2.5 plus
yeah.
minus 4.5. Yeah.
Never mind.
Okay. Okay. So that is pretty much the Mohr circles, and you can just go to the practice, and Mohr circle techniques can be applied. Right now I'm talking about is a little bit new topics. The Mohr circle is for two-dimensional stress. We call it plane stress. And the plane stress basically is here we are only given the sigma x, sigma y, and tau xy, and there's no component in the z direction. Mohr circle can be applied, is able to apply to the three-dimensional case, and that is a new topic right now I'm talking about. But that has a certain limitations. So let me write it up here. So general 3D stresses, we are given the sigma x, sigma y, sigma z, and tau xy, tau xz, and tau yz, and tau yx, and tau zx, and tau zy. Okay. So in general, we have the 9 components, and that is what we define as the three-dimensional stress element. So this is a 3D stress. Mohr circle wouldn't be able to 2D Mohr circles cannot be applied to the transformations of general 3D stress, but it can be applied to the transformations of something. I'm going to write up the graph and then write it down the statement.
Excuse me, Professor.
Yes.
On your 3D stress, the top shear stress, what is that?
Yeah, so this is tau yx.
Yx.
Yeah, in the y plane pointing to x direction. So, for example, a specific 3D stress like this. X, Y, Z. And let me make one case. Say, for example, let me make one case and let you tell what is this. 10, 2, and say 4. So for this example, this is a very special condition for 3-dimensional stress element. And anyone can tell what is the features in this example compared to the general statement here. All the string stresses are 0. for this example, right? I raised up this example because this example is so spatial. Why it is spatial? Because it has no shear stress. And there's a no shear stress per our definition in this specific angles or orientation. It actually is in the principal orientation of the 3D stress. So basically here I'm showing 10 to 4 are the principal stresses of this condition. So this is in principal directions, and 10, 4, and 2 are the principal stresses, and where no shear stress. So the Mohr circle can be applied to the transformation of the 3D stress in its principal directions. Okay, so you keep this in mind, and Wednesday, this I will. This is a very, very simple step, and this is much easier, graphically, much easier and cleaner than this one. And that is one step of the little applications of the Mohr circle. But again, that has a limitation. As long as you have described your three-dimensional stress in the principal orientation, then you can apply Mohr circle. Otherwise, you could